Good morning. Last 6 classes we talked about heat treatment of steel, and today we begin a new chapter, new topic. We will look at surface hardening. Now, under this we will try and see why do we need surface hardening, and one of the reason we may say it is quite evident when we talked about heat treatment of steel. Say if we want to harden it, often it is not possible to get uniform properties from surface to the core because of the limitation of the cooling rate that we adopt. Even if we quench, if the dimension is large, uh, the core will may cool depending on the dimension of the job. The core may cool very slowly. You may have a totally different structure and properties at the core, whereas you may have extremely hard structure at the surface. And in surface hardening, we actually try to exploit this feature, and we will see why do we need, what are the types of component where we need surface hardening. We will look at some common methods of surface hardening. We will talk about induction hardening. We will talk about that a carburization process, case carburizing. We will talk about post carburization heat treatment, case and core refining. We will also look at the residual stress pattern that is likely to develop as a result of surface hardening. We will see whether it is when it is beneficial, when it is harmful, and we will also talk about another process of surface hardening called night riding. Now, main purpose of this particular course is to correlate the material and the processing behavior and processing technique which is adopted. The material means basically we say that composition of the material, what the material consists of, whether it is a pure metal or it is an alloy, what are the alloying elements added, and how do we process, whether it is cold rolled or whether it is annealed or whether it is cold rolled and recrystallized structure, or whether it has been given some special heat treatment or some thermomechanical processing that will affect its properties. And whenever we select a material, it has it's with a specific objective, it has to perform well in service. Now, this performance criteria may vary from component to component. For certain component, we will look at certain specific properties. Say suppose if we are selecting a material for cutting tool or hacksaw, what we will look for, whether the material is extremely hard, can be hardened so that it can cut most material. So, in that case obvious choice will be, say suppose we say that plain carbon steel, because hacksaw is quite thin, you can quench a plain carbon steel, say having a high carbon content, and you can get fully martensitic structure, give it a low temperature tempering, and it will have a very high hardness close to RC64, and with this you will be able to cut most metallic materials and many other non-metallic material as well. So, here the performance, the processing is actually apart from the making the sheet of the thin sheets from which by thermomechanical processing from which a hacksaw will be made, another important processing is heat treatment. Now, we will see some examples also in as we go through this lecture. And in fact, when if we look at a real component, it always has a particular dimension, and very often these dimensions are quite large. So, one of the common structural component that you may have seen is I-beams. Say it is used in bridges, it is used in multi-story construction of multi-story building, and there you will find the section has a different dimension in different zone. This I-beam, this is the flange part actually, and this is the web part, and this is the top flange, this is the bottom flange, these dimensions are same, and this is web is relatively thin, and these are made by section rolling or hot rolling. and this rolling is done quite in a high temperature. The steel is maybe around 1200, 1100, 1200 to 1100 degree centigrade. It is rolled into this section, and after that it is air cooled. Now, since this section size here is small, when it is air cooled, you may find that flange will cool, the materials in the flange will cool relatively slower compared to the wave. So, therefore, what you expect that the wave will have finer paralitic structure, it will be stronger, whereas the flange will cool slower, it will have more amount of pro-eutectoid ferrite, it will have relatively coarse paralitic structure. Therefore, this strength will be low and this part will have a higher strength, and usually we find that normal processing you will find that this will have a high strength, this has an associated along with it ductility may be relatively low compared to this. Now, the point is this is obviously this is. So, here although the designer may speak properties based on the wave, but actual that most critically stressed region is the flange. So, that is why it is made thicker. So, this is where we learn to live with it, and in surface hardening. So, this is not intentional, this is because of the size limitation you get different properties, and whatever and whenever you design an I beam you always see that this is the least stress. So, you make it thin, this is the high stress region. So, you make it thicker, so that the stress is much lower than the permissible level of stress for this particular material. Now, we try to develop dissimilar properties, means we are in case of a surface hardening we try to exploit such a feature. See, if different regions are cooled differently, you can get different properties. If you cool surface very fast, then you will get a very hard structure at the surface, and many applications we do need such material. So, here you can see we have listed why surface hardening is necessary. So, there are several components like gears, shafts. Some of these drive shafts may be very huge, very large, particularly say steam turbine for power generation. They are extremely large. I mean the diameter itself may be half a meter diameter, and the length also may be quite long, maybe 10-15 meters long, and such a material is to be given and it rotates. Many of these components they rotate at very high speed. So, therefore, the surface is highly stressed, and it is also the steam passes through it, it is also supposed to have good wear resistance. So, materials like this gear, shafts, there you need high wear resistant surface, and it must, and at the same time it must have a soft core, because core the stress is not very high, but if so therefore, it is better to have a soft and tough core, so that even if a crack initiates at the surface, it does not propagate, leading to failure. Now, problem is difficulty to get hard surface in large sections. Say like gears, some of these gears the section size is quite large, shafts are indeed a very thick component. So, here it will be impossible, virtually impossible to get full hardness by quenching that whole component. Not only that, when you quench a very large component, that thermal gradient will be so high that it will be thermal stresses will be very high. Along with it there will be superimposed transformation stress, and that can result in cracking during because of thermal shock as well as for the transformation stresses, and you get unfavorable residual stress pattern if you try to harden such thick components. Now, how can we do surface hardening? So, there are several methods, We will not go all of this, and I am told there is a separate course on surface engineering. So, therefore, we will talk some of these which are related to steel. See, some of these which are listed is a short pinning. It is a general method. It is applicable to all metals. Like steel, we have seen it is amenable to a large number of special heat treatment processes, because it undergoes allotropic transformation. It has a certain special, that phase diagram has certain very specific feature which makes it amenable to a large number of different heat treatment processes, which may not be so in many other metals. But short pinning, where you try to say some hard balls, they are allowed to they at a moving at a very high speed is allowed to strike the surface, and the surface gets cold work. There is a local hardening, and which results in increase in strength of the surface. Now, there is another way of doing it, that is heat, that is local heating, heat only the surface and then cool at fast. So, this is applicable to steel, and here you do get very high hardness. We will talk about it in little detail. There is another, see, normally in order to have a low tough core, it is often necessary that you have low carbon in the core. So, low carbon in the core gives you very good toughness, and you can also give some special hardening treatment, special heat treatment, by which you can indeed improve the toughness of the core by making the cementite, which is actually present, that carbon is mostly present as cementite, and if it is present in paralitic, it may not have that kind of a toughness, but if you can give a special heat treatment by which you can break down the plates, cementite plates in paralite into small globules, then what you will have a dispersion of globules, fine globules of cementite in a ferrite matrix, and that type of structure has very good toughness, and also they can be machined, they have good machinability. Many large components are first given this kind of a heat treatment, spheroidizing, annealing, they are machined, and then finally, the surface hardening heat treatment is given. And let us see, and in that case, if you have low carbon content, even if you heat the surface and quench, you may not get the desired hardness. So, therefore, you need to modify the composition of the surface. So, you need, and this is done by some amount of, by diffusing that element which can increase the hardness of surface, and then subsequent heat treatment. And apart from this, there are lots of other coating processes where you can give hard coatings, and usually coatings are there are multi-layer coatings you may have to give to maintain the compatibility with the base material. You may have to give several layers of coating, bond coat, then you have and ultimately you will have a hard, that resistant coating, wear resistant coating, or some material you want a thermal barrier coating. So, different types of coatings are possible for different types of applications, but we will not go into the details. We will concentrate on, because these two are related to heat treatment of steels, and bulk of the components that we use, they are made of steel. Now, one such heat treatment process is induction hardening, and in induction hardening what you do is you heat the surface, that is local heating. We will see, apart from this, there may be some few other methods of local heating, but let us concentrate on induction hardening, and here you heat the surface by induction heating, put the job within an induction coil, and it gets heated because of the eddy current of that high frequency AC, that current that flows through the coil, and it gets heated to the austenitic region. Here core does not get heated because of that alternating current, because of the skin effect, the core does not get heated and structure remains unaltered. surface and then surface after, since it has converted into austenite, if you quench the surface many times, the quenching facilities are also built in along with the coil. After it has hardened, you can quench by spraying water or any other quenchant, and so therefore, you can get martensite on the surface. So, one of the main characteristic of this is very fast heating, and the time is very short, that whole time is very short. So, therefore, what we may need, you may need a little higher austenizing temperature than a normal hardening process, and then martensite that forms will be forming in very fine austenitic grain, and this austenite grain, to make it homogeneous, also we have seen that this is a diffusion control process. If hold time is very short, it is quite likely that this austenite may not have homogeneous, that austenite grains may not have homogeneous composition. It may have different carbon content in different region. There may be some amount of undissolved carbides also. So, therefore, that martensite that forms will be forming in non-homogeneous austenite. There may be some amount of undissolved carbides, but which may give, and because of all these combination, it may often have higher than expected hardness, that higher than hardness that you normally would have got in the steel having the same carbon content. And this treatment can be given to carbon steels also, plain carbon steel. This may not have any alloying element, any intentional alloying element to improve hardenabilities may not be required, even simple plain carbon steels within, but it must have little high carbon, because if you want high hardness at the surface, this hardness is determined primarily by carbon content in the steel. So, it should have a relatively high carbon content, and since only the surface is being heated and the heating time is also very short. So, see, normally when you give a heat treatment, if there is a long soaking period, then the surface gets oxidized, surface finish is disturbed, but here the heating time is very short. So, therefore, it retains good surface finish. There is little distortion because the total heat content is also less. And this, in this particular slide, we have a particular describes, this is a high frequency alternating current source, and this is the coil, and usually these coils are water cooled, and here is a job and which gets heated, and it is we have tried to show diagrammatically. When it heated, this is a sectional view, the core central region does not get heated, it is the surface that gets heated, and after it gets heated, that the depth of hardness will be determined. This is a particular expression which describes the relationships between the depth of hardening and your parameters which you can control, and what you can control is the frequency of the current. And if you use a very high frequency, because of the skin effect, the thickness, the depth of hardening is low. So, depth of hardening can also be increased by increasing the hold time also, because if this gets heated, then this heat will get transmitted, that get conducted toward, it will move towards the core also. So, if you have a longer heating time, maybe the thickness, depth of hardening also you can control. So, by controlling the frequency, controlling the hold time, you can control the depth of hardening, and this is primarily depends on that principle of heating is because of eddy current. So, therefore, resistivity is an important factor, and it will also determine by the flux linkage. So, that is which will be determined by the magnetic permeability. So, obviously, with a high temperature in austenitic region, it will be little low. So, but in the initially it is quite high. So, if it is low, in that case you can see it is inversely proportional to this. So, high permeability means low depth of hardening, but in the austenitic it will be relatively low. And So, main factor which you can easy to control, because these two are material property, you may not have many option to play with, but what you can play with is the frequency and hold time. And on quenching, after it has reached the particular, it can be automated also. You can have temperature measuring devices, and immediately after this it reaches the temperature, you can start water spraying and it is cooled. And since and during cooling, you know, the heat will be flowing outside as well as it goes inside as well. Now, let us look at that structure within where I mean in a induction hardened steel. Say here, if you look at this part where I said, in order to get good a tough core, it is previously given a spheroidizing annealing, and this diagram which shows the usual spheroidizing annealing temperature, and usually if you keep around this eutectoid and if the temperature is slightly fluctuating, it gets spheroidized very quickly. That cementite platelets, that means cementite plates and in perlite. So, this is the cementite plates in a perlite, and if you keep it for a little longer, this breaks down into globules, and by this it is possible to have the totally globular structure within this. See, and in microstructure, of course, if these particles are very small, they may look like a dark, and if it is nitrile etch, usually they will look like this type of globules, only the boundary will be etched and there will be such globules all through. An amount of this cementite will depend on the carbon content. By this spheroidizing annealing, you get a very tough core, and it also helps in machinability, and after the full machining you give induction hardening. And here let us say only this is the area which gets heated. This is the area which gets heated. So, the during heat this induction hardening, the transformation will be localized. So, only this area has been heated. So, you expect transformation here, and look at what is the temperature. Now, you have to convert it into austenite. So, therefore, if this is you have to heat it in the austenitic region. Let us say this is the critical temperature. Say let us say in the surface the carbon content is around this. So, this is the critical temperature, this is A1, and A3 will be little over this, but you will try to heat it at a sufficiently high temperature, because your time of hold time will be very short. Because of long hold time, your purpose of surface hardening will be lost, because heat will strike and flow inwards and make this case very that heated section will be much thicker, then you may land up in problem. So, what happens here, you have to heat it to a little higher temperature, and then you have to adjust your time. So, here maybe the austenite first appears, here you have austenite plus ferrite type of structure, and but you may also have some amount of cementite also present. Here you may have some austenite plus some carbide cementite, and here possibly you have inhomogeneous austenite, and here this line beyond this you will get homogeneous austenite. But often this time may be very long. So, one way of heating it, maybe you heat it to a relatively higher temperature, short time, you may and you may have to quench from this region. So, that is why, since you have to use much higher austenitization temperature, as held time is very short, and when you quench after it has reached that particular temperature, kept it for certain length of time, you quench, that means by spraying water, water spray, you quench, and this usually the quenching rate will be very fast, and in this high carbon steel. So, if it is a high or medium carbon steel, you will get plate type of. So, these are like this kind of an acicular shape plates type which develop, which partitions that austenite boundary. So, initial plate will be longer and subsequent plate, and this will be totally athermal, and entire structure will be converted into plate martensite, and it will have a very high hardness. And since this is a plate and this is an unstable microstructure, so it needs a little bit of tempering, and in fact, it can be automated after you quench, and you can same coil, heating coil can also be used to heat the surface, but this time you heat it to lower, and here lower range, and you can give the tempering. So, this is a very highly automated and easy and can be easily implemented in mass production. And when you do this, we will see later also, not only you develop a hard surface and tough core, but you also develop compressive residual stress at the surface. And always whenever you have a residual stresses develop in a component because of local plastic deformation, and whenever in a region you will have compressive stress, there will be in certain region you must have tensile, and in fact, in the core there will be tensile stress, and the components where particularly in shaft that core the stresses will be very low. So, therefore, you can afford to have little tensile stress at the surface, but at the core, but not at the surface, because surface is the most highly stressed part of the component. Now, the problem comes up when you try to harden a steel where the carbon content is low. Many times for many application, particularly gear. So, you want that gear it to be quite cheap. So, if it is made up of mostly plain carbon, it will be quite cheap. So, if you have a low plain carbon steel, say having not more than 0.15 carbon, and then if you can somehow enrich the carbon content on the surface and then give heat treatment. And in fact, this is the most common heat treatment which is given to gears and heavy duty gears. And here what is done, there are several types of methods by which you can increase the carbon content at the surface, and one very popular method is back carburizing, and this treatment is given to low carbon steel. So, here you have a material, say suppose this is the job which is kept in a mixture of carburizing mixture, which is made up of activated charcoal, say around 85% charcoal, and you also need some energizer, 15% energizer to promote carburization process. And how does it promote carburization process? When you heat it to higher temperature, maybe 900, around say 950 degree centigrade, what happens? This barium carbonate, and this is a packed bed, and in fact, this is you do not have enough oxygen, when this oxygen is only limited to the extent which is that air which is trapped within these spaces between charcoal particles and the energizer. So, what happens here? This primarily you get oxidizing it, how do you get this carburization? This barium carbonate decomposes, and you do not have enough oxygen here. The CO2, there are plenty of carbon. So, CO2 will react with carbon to form carbon monoxide. So, surrounding this, say surrounding this particular job, say if you look at here, surrounding this particular job, you will have an environment, a gaseous environment, which will consist of primarily CO and CO2, and in fact, the CO in presence of steel at the surface, it decomposes into this, and this carbon, this is a nascent carbon which has very high activity, and this can get this is an interstitial element, and at 950 degree centigrade iron can dissolve large amount of significant amount of carbon. So, it diffuses very fast and moves into austenite, and this is the reaction, main carburization reaction. So, two things you have at your disposal to control the extent of carburization. One is the temperature. Higher the temperature, higher will be carbon content at the surface and faster will be the reaction, and also you have to allow the carbon time to allow you need time for carbon atom to diffuse, move into iron lattice. So, therefore, you have to allow certain amount of time. So, this is dependent. So, depth of carburization will be a strong function of both temperature and time. Now, the question comes to what temperature will you heat it to? Now, suppose if you heat it to a lower temperature over here. So, now the problem is at this low temperature, first is solubility of carbon in ferrite in this region is very low. So, ferrite can only very limited amount, which is possibly less than the carbon content which is already there. So, this ferrite is saturated. So, it cannot absorb much carbon. So, you can't. So, now the question is, can you do a carburization over here, but the problem is here if you heat, it will be a two phase structure. At this temperature, the structure will be made up of here, if you look up here, it is made up of ferrite plus austenite. Yes, of course, austenite can dissolve high amount of carbon, but not ferrite. So, if you have on the surface you have ferrite grain, you also have austenite grain. So, you will find the carbon will diffuse more here and very little over here, because ferrite solubility is very little. So, here again the problem will be that carbon distribution is not likely to be uniform in the structure. So, this is a problem. So, obvious choice will be you have to heat it within this austenitic region, and better is you keep it a little higher temperature. So, where mobility of carbon atom diffusion coefficient is high, and say this is the temperature, so maybe around 950. If you heat, then the austenite can dissolve up to this much amount of carbon. So, this carbon content at the surface will primarily be determined by this temperature at which you are performing back carburizing operation. So, this determines surface carbon content, and the depth of carburization will depend on the diffusivity of carbon. At higher temperature, it has higher diffusivity. So, therefore, high temperature will have will actually high temperature will higher the temperature will higher will be the depth of carburization and higher carbon content at the surface. And the process of mechanism is illustrated here. If you heat this in a carburizing atmosphere, what you have, you maintain a high carbon concentration at the surface, and here you have high carbon concentration, whereas at the core this is a sectional view, and so carbon here, and so there is a concentration gradient, and carbon will diffuse from high concentration to low concentration. So, you will have a concentration gradient which is shown over here. You have maximum carbon content at the surface. As you go inside deeper, the carbon content will be lower. So, you will have this kind of a plot, and if you hold it for longer time, same temperature carbon content at the surface will remain same, but the depth of hardening, the depth to which the carbon concentration increases, that will increase. So, like here this is the depth, whereas here this is the depth, let us say. And it is possible, we learnt about diffusivity, the process, and how to calculate this depth of carburization. And next slide we illustrate that. Say suppose we assume this as a 1D problem, you maintaining high carbon content at this surface, and this is and this is the core where you have low carbon content. So, this is the position at time t 0, but with time the carbon will start diffusing, and we have seen that this carbon concentration at any instant at any position will be, this is the carbon content C, whereas this is the initial carbon content of the steel, this is the carbon content which at the surface. So, this is given by this error function, where x is the distance from this end where you have high carbon concentration, and d is the diffusivity, t is the time. And in fact, the diffusivity is given by this type of expression. So, this is the diffusivity of carbon in gamma iron. So, this is the frequency factor, the d naught in of carbon in gamma iron, and many of these are have been experimentally determined. So, it is actually possible to calculate also, and it is also not difficult, and we can even make some approximate calculation. So, if we assume that if you look at this sheet here, so here if this is the surface content, somewhere in between you will have average carbon content. And if we define that this is the depth of carburization, then it is quite easy to find out this depth of carburization using this equation here, and we know that error function around, if this value, this z is around 0.5, then error function is equal to 0.5. So, that is why you can say if this is equal to 0.5, because if you put C as C, as I have explained, if you put C, this you equate it to C and substitute in that equation for that C minus C naught, here in this equation error function here, then you will find that this comes out to be 0.5. So, obviously, then x over 2 root over dt, this is equal to 1 over 2. So, therefore, depth of carburization is approximately equal to root over dt. And here is a problem we can try. So, the temperature is given, the time is over here, this initial, the C naught is given, the activation energy for carbon in austenite, the diffusivity for carbon diffusion in austenite is given, and the surface concentration of carbon is this, and try and estimate the depth of carburization. And then if you estimate the depth of carburization, and you can say that here what will be the amount of percentage perlite, you can in this find out how much will be the percentage of perlite over here. If you look at the microstructure after this carburization heat treatment, if you look at that microstructure, you will find so there will be a thin layer, some carbide also, in some cases it is reported you may have a thin layer of which will be brittle, and during quenching and all that it cracks and gets removed. So, there may be a cementite, and after that here you will have you will have a network of this bright network which will be made up of cementite network, and as you go inward that cementite network will become thinner, and there will be a region where it will be mostly perlite, 100% mostly perlite, and sometime it is possible to guess from the cementite network what is the austenite grain size, prior austenite grain size of this material. And as you go downward here, that structure will be mostly ferrite plus little amount of perlite depending on the carbon content. So, you will have a structure gradient, means structure will vary from surface to core. And now let us see there are certain limitation in pack carburizing. In pack carburizing, of course, it is very easy. You pack it in a box consisting of that carburizing mixture, but here after you have done the carburizing, you can't, like in induction hardening, after it has hardened, you can spray water, you can cool, you can quench, but here it is not possible. So, this is a major limitation. Second is the temperature control is also a major limitation. So, by pack carburizing, you have some poor control over temperature and carburization depth, and also you cannot directly quench. Direct quenching is not possible. So, to improve the productivity, depending on whether job sizes are small, so many cases people prefer gas and liquid bath carburizing. What are these? So, essence is you have to heat the job in an environment where with a high carbon potential. So, one way of doing it, you can heat it in a carburizing atmosphere. A very common gas mixture is around 15 to 20% methane with some neutral gas carrier. It could be nitrogen or argon or which does not react with steel. So, it could be nitrogen is quite cheap and quite popular. So, you can use that, and under this condition this methane in presence of iron, it cracks, and this is that carbon which deposits, and you also get hydrogen. So, it maintains a reducing, it does not oxidize. So, you have a good control on the surface quality, but you need to avoid high concentration of this carburizing gas. So, you should not allow soot formation, and also say avoid, you have to avoid also high velocity, because you have to allow some residence time you have to give. If you allow, so avoid high concentration, high velocity, but this can be controlled. Many of these temperature control devices can be adopted. You can also have flow control devices, and so you have a very close control over the process. So, it allows close control, and so on this depth of carburization, on temperature, and also it allows direct quenching facility. So, in certain cases it cuts down the post carburization heat treatment cost. Similarly, liquid carburization is another alternative process where you have the job is heated in a salt bath, and these salt baths are usually chloride bath, which are say one common composition is around 82% barium chloride, 10% sodium chloride, and you have add sodium cyanide. So, this is the source of carbon, and in fact, the reactions which are given here, this barium chloride reacts with this, forms barium cyanide and sodium chloride, and this decomposes near the steel surface and giving this nascent carbon, and which dissolves in iron, and at this temperature is around 900 or 950 degree centigrade, where this will be austenite, this will be in austenitic state. So, obviously, you are dipping the job in a liquid bath which is already heated. So, there is a rapid heat transfer, the process is quite fast, you have a better control on temperature, and you can after this that certain time, you hold time, you can take out the job and quench in an appropriate quenching medium. So, therefore, this method has become very popular, but now the problem comes up when you do carburizing, you are heating it to a relatively higher temperature, and when you heat a steel to a relatively higher temperature, say suppose in pack carburizing, you are heating it somewhere here, which is much above, say normal heat treatment temperature is around here. So, you are heating it here, so that you have that carburization process is faster, carbon content at the surface is higher, and after that what happens if you quench it? Here you have a very coarse grain structure, coarse austenite grain. Now, we know the coarse austenite grain, if the austenite grains are coarse, the site for perlite or diffusion product to form, that reduces. So, therefore, its hardenability increases. So, it is quite likely after this, if you directly quench from this particular temperature, you may have problem. Sometime the core can also get hardened. So, usually this is avoided, but certain cases if you make sure that if this steel is such that and you have a good control over hold time, certainly not in case of a pack carburizing. This process is ruled out in not in pack carburizing. If it is a pack carburizing, in any way direct quenching is not possible. So, pack carburizing you have the heat, a very complicated heat treatment sequence, but in case of a liquid carburizing or gas carburizing, there is a possibility if the steel is fine grain, then such coarse grain will not develop as it develops in pack carburizing, and there you can quench directly and save lots of subsequent, you do not have to go through subsequent heating treatment, and after that you just temper and use. So, this is possible in fine grain steel, as usually such steels are aluminum keeled steel. This kiln steel, here aluminum is added, and this aluminum reacts with the oxygen present in molten steel and forms alumina, and these alumina they block the grain boundary movement or migration of grain boundary. So, this is important. So, depending on the type of steel that you have, you can choose, and if you are selecting gas carburizing or liquid carburizing, you can directly quench after carburization. But in case of a pack carburizing, it is not possible. You have a very coarse austenite grain at the core, you have a case carburized portion, here you have a high carbon content, and because of this they also have different MS and MF temperature. Now, you have to give to this type of step treatment. After this, so this is the carburization period, where here it develops coarse austenite, and in pack carburizing there is no way you can quench, you will be cooling slowly. So, that is the time in the core also core you will have coarse austenite grain, but it will be made up of, core will be made up of ferrite plus perlite, but prior austenite grain size will be coarse. Whereas, case has a high carbon here somewhere in this region, and if you are cooling, there is a likelihood that cementite network will form. So, core may be, because of the slow cooling, you may have a case may have brittle cementite network, which is undesirable. So, therefore, you got to refine first core, refine core by heating it above this temperature. So, this is normal A3 plus 20 to 30 degree centigrade, hold time, give sufficient hold time, then you quench, and that is the time you can refine, since you are suppressing this cementite network does not form over here. This also gets converted into possibly you will have globules of cementite or broken cementite network in case, and finally, you give case hardening treatment, and here you heat it to this temperature, because this case is hypereutectoid. So, you heat it to this temperature ACM plus 20 to 30 degree centigrade, and after that you quench. So, you will have now the final heat treated structure. So, this is shown here, exposure to high temperature listed gives a very coarse grain structure in the core, and to get best combination of hard case and tough core, multiple stages of heat treatment may be necessary. So, this is why we talked about core refining, talked about case refining and hardening, and both cases here the core refining you have to heat it in this region, quench, and in case of case hardening you come here and from this temperature and then you give the final heat treatment. And in inherently fine grained steel, the steel can be directly quenched, but it is not possible in pack carburizing. And this I think during the final hardening, of course, this has a final hardening, even if the core you are here. So, what you will have, it is predominantly ferrite plus some amount of austenite. This austenite, even if it is gets transformed into, there is a possibility it can be depending on the section size, but it will still have within a soft matrix you will have a hard phase which is martensitic, and it will give a very tough core. It will still have a very tough core, and after this you also need to give some tempering heat treatment. And one of the important thing in this type of hard heat treatment is the development of favorable residual stress. Why do you get it? And which is shown over here. You have a surface and the core, and they have different carbon content, which is shown over here. Schematically I have shown, this is a low carbon, this is core, this is case. So, these are I think this is we will look at this over here. There is look at this over here at the core, this is the MS, this is MF. Similarly, case, this is MS start of martensitic temperature, this is MF. Now, you have different cooling rate. When you are quenching, this is the surface cools slower. So, this is initially temperature is same and final also temperature will going to be uniform. So, you have this kind of a cooling rate or cooling curve, and this is the case. So, case cools much faster, whereas the core cools much slower. Now, what happens? Where does the transformation takes place first? You look at it, when the case reaches MS temperature, the core temperature is quite high. High temperature means it has low strength also. So, when this core is transforming, the when case is transforming, core can accommodate the deformation associated. It can plastically deform because it has it is still very hot, it is plastic. So, therefore, what you have in this situation, the case transforms first and it becomes hard, and after it has become hard, then the transformation at cores starts. Now, the core will try to expand. If the core at this stage tries to expand, see here, if the core which is low carbon content, if this is trying to expand, this will not allow it to expand. So, therefore, this is trying to expand. So, therefore, this will be subjected to this case transforms first when the core is still hot, whereas the core transform last when the case is cold. So, therefore, you will have a residual compressive stress on the surface. Now, another important heat treatment, surface heat treatment is nitrogen. Also, you can allow nitrogen to diffuse into the system. The process is exactly similar, and this is done with the job is heated in a cracked ammonia environment, and the temperature is much lower than the lower critical temperature. That means, maybe around 500 say in this temperature region, if you heat, and then the carbon diffuses and the nitrogen also can diffuse into steel, and it can give this kind of hardness level. And therefore, and here and this hardness level that can be very high. whereas RC hardness around 65 is around say 850 VPN, Vickers hardness number. So, imagine by this you can increase the surface hard to a very high level, but often you can form a brittle this nitride layer, and which is harmful, but this you can control by controlling the process. Also, even if it has formed, later on by lapping, by polishing, it can be removed, it is detrimental. And but if you can control the partial pressure properly, it is possible to avoid formation of this brittle layer. And this type of treatment is very popular and given to different types of steel, and there is a special type of steel, nitralloy, where you do get a very high hardness, which is shown over here. This is hardness against time. So, this is, and the depth of hardening also will have a similar type of profile. As and normal plain carbon steel, you do not get that kind of effect, but if you have these alloy elements, particularly the chromium, particularly if some aluminum is there, aluminum nitride also, aluminum nitride is also very hard, and they add to the surface hardness, and presence of this nitride forming elements, this increases kinetics of nitriding. And it will be interesting to look at the iron nitrogen phase diagram. You have normal nitrogen nitriding treatment in this region, and this is the gamma prime, which is very brittle, and we should try and avoid this. And main reason for this is you have a favorable surface hardening is on fatigue life. Many of these rotating components are given this treatment, and which is shown over here. This is the endurance limit. It increases by giving this kind of, this is the effect of short pinning, this is nitriding. Many shafts are given this nitriding heat treatment, particularly this high performance, this turbine shafts are given this kind of a treatment. So, therefore, to sum up what we have looked at the non-uniformity of structure, in uniformity structure properties, limitation of hardening treatment, advantages of surface hardening. We talked about case carburizing, nitriding, origin of residual stresses, and its effect on extending fatigue life. Thank you very much.